Hi, everybody. Welcome. We'll get started in about 5 minutes. Just gonna wait for people to trickle in.
Yeah, we are almost there, I think. Okay, give me another like 1 minute or so. I'll just. Okay, I think we are here. Hello everyone. Thanks for joining today's webinar. And today's webinar topic is AI research for building performance simulation, presented by the ibpsa-usa Education Committee. And my name is Liang Zhang. I'll be your moderator today. While waiting for another moment, maybe for other attendees join, I would like to go over some housekeeping notes. Today's session is being recorded and will be available on ibpsa-usa's YouTube channel and shortly after the event. If you experience any audio issues, we recommend switching to phone audio instead of computer audio for the better connection. This is a Zoom webinar, so we invite you participate by using a Q&A feature at the bottom of your screen. You can submit questions at any time. Questions are visible to all attendees. You can also choose to submit anonymously, and feel free to upvote questions that resonate with you. We will address all the most popular ones during the Q&A portion at the end of the webinar. At ibpsa-usa, we are committed to our mission of fostering better buildings through simulation. We welcome your engagement and questions and ideas as we explore this exciting topic. So I'm going to introduce today's speaker, Dr. Liang Zhang and Dr. Rishee Jain. And they will present their work for about 15 minutes each, and which leaves us about another 20 minutes for discussion and questions. During those discussions, you can unmute yourselves if you wanted to, or type in your questions. That's fine too. Our first speaker is Dr. Liang Zhang. Dr. Zhang is an assistant professor of the Department of Civil and Architectural Engineering and Mechanics at the University of Arizona. Prior to joining the University of Arizona, Liang was a research scientist at the National Renewable Energy Laboratory, where he led and worked on high-profile U.S. Department of Energy projects related to large-scale buildings energy modeling, artificial intelligence in buildings, smart and connected communities, and fall detection and diagnostics. And our second speaker is Dr. Rishee Jain and his PhD student, Dipashreya. Dr. Jain is an associate professor of civil and environmental engineering and the director of the Urban Informatics Lab at Stanford University. His research focuses on the development of data-driven and social technical solutions to sustainability problems facing the urban built environment, and lies at the intersection of civil engineering, data analytics, and social science. He's a recipient of the Career Award from the National Science Foundation and a Building Innovator Fellowship from the Department of Energy. Yeah, please join me, give a warm welcome to the speakers. And Dr. Zhang, if you can start share your screen. If you
Okay. Thanks, Yuan, for the introduction. So I'm sharing my screen now. Can you see my screen?
Yes.
Okay. So yeah, good morning and good afternoon, everyone. My name is Liang Zhang, and today my presentation about towards BEMGPT, a fine-tuned large language model to learn BEM documentation for education and training. My presentation has 5 parts. First, the background of generative AI and AI in BEM education. The second is our fine-tuned model BEMGPT development. Third is introducing its performance and discussion. Fourth, about how we open source it. And finally, the conclusion and the future work. The generative AI and the AI has been more and more widely used in building energy modeling, including the full life cycle. So you can see that generative AI or AI can help with processing the input data for the modeling by converting the unstructured data to structured data, and also can enable the enhance of the BEM workflows. So basically, like automating a lot of procedures that used to need expert knowledge. It can also use its coding capability to actually analysis its output and visualize its result, and also draw some conclusions based on that. Among all these components, actually education and training is the one component that can be most benefit from the generative AI. This is because generative AI is so good at knowledge extractions and summary, and this is will be very beneficial to BEM modelers when they learn to use BEM. So in order to understand how that works, so I first put here a pyramid of about the theory to practical spectrum in BEM education, meaning these are the different layers of knowledge that BEM modelers need to become a good energy modeler, which includes the fundamental part, which is the building physics, including the components like air heat balance, the heat transfer process through the walls, HVAC components, the refrigeration loop, and also some codes and standard. So in the middle is about is also an important part about software specific training, is about that you need to be familiar with at least some software to know its like interface, navigation, the syntax of preparing its input, and also some options in the simulation. And on the top is about more about the workflow specific training, which is about because BEM includes multiple steps or procedures, so that you will have to gathering like input data and then build models and then analyze its results. So it's more like workflow specific, which is often useful in the company workshop or training or on the job mentoring. So generative AI can be benefit in terms of these 3 perspectives to benefit BEM education and training. The first is about the interactive document and Q&A, because the beginners who just start to use BEM will be very access to massive of knowledge, like thousands of pages of documentations and the knowledge from here and there. So generative AI will provide a full interactive like environment to help them to ask and search information in a very interactive way. And at the same time, there are a lot of like not just documentation, but also some online resources, just like Unmet Hours, which is a Q&A like a website that people post their questions, and the expert modelers will answer questions accordingly. So generative AI can actually gather this online like Q&A information, like to really benefit the modelers to actually access this knowledge in a very quick and efficient way. The second way of Gen AI can be used in BEM education is about training material generation. As I mentioned, the BEM education includes about building physics, the software specific training, and workflow training. So meaning that there are different audience or different education outcome for different like training purposes. Generative AI can be very useful in terms of creating the like training material like tailored to these different education outcomes, or the adapt to different learner skills levels. And the third is about it can be a good modeling tutor. Generative AI, just like GitHub Copilot and the Cursor, can help programmers to actually be coding in an interactive way, can give them hints on the code or just code for them or prepare parts of the code for them. And similarly, that a modeling tutor will guide the modeler through simulation with feedbacks. It will tell the modeler, explain the errors or some complex model logic that they so that it can facilitate or improve their learning experience when they're trying to understand learned BEM. There are a lot of opportunities of generative AI, especially large language models, which is one of the core area in the generative AI. Because the large language models can very easily extract, understand, and summarize domain-specific knowledge in a very efficient way. At the same time, another technique is called the retrieval augmented generation, or RAG, further improves the large language model's capability by accessing external data set so that it can more accurately getting information by external resources and also improves the LLM by providing more truth grounding. But still, there are challenges. One of the challenges that the foundation model or general foundation models are sometimes too large with unnecessary information, and the parameter space is super large, so that it'll be very expensive to use. And second is that it needs integration with external data, like you need to give it external document to let it learn. So both of them will lead to more expensive use of a large language model. The second is that we not only just retrieve knowledge, but we also hope that the foundation model can reason like or think like a building energy modeler or a BEM expert. So the reasoning capability are essential for large language model agent development, which is also a very key techniques that to automate the workflows using large language model. So this challenge points to a technology which is called fine-tuning, or actually one of the big topic in this presentation, because fine-tuning is one of the most cost-effective techniques to inject knowledge to a foundation model, and also can enable the model to have the reasoning capability. So actually, fine-tuning is not it's actually everywhere. For example, your ChatGPT is actually fine-tuned based on GPT-3. By embedding to have a more capability to chat and give a more be more responsive to questions. And also the codex, which is the core of the GitHub Copilot V1, is actually fine-tuned based on GPT-4 by learning from all the public GitHub repositories and learn how to code, and then embedding the coding capabilities into the foundation model. So fine-tuning basically can achieve two goals. The one is gain knowledge, which is very obvious that it can inject external knowledge to the foundation model to learn something that they have never been trained on. The second is about the behavior change. So it can learn to respond in a more consistent way, like to be more professional, be more helpful, be fitting into different use case scenario. But at the same time, it can have the ability to better at the conversation or even better at the reasoning. So good fine-tuning basically have these two ability at the same time. So next I will introduce how we develop our BEMGPT. Before we go to technical details, so this is an analogy I make to fine-tuning a model just like a teacher student, that the recipient of the knowledge is a student and it learn from textbooks with equations and images. And also the teaching methods can be, you can give it a lot of content or very few or high quality content, or you can be in a very strict way or very freestyle. And the outcome will be a student not only can know the knowledge, but also can apply knowledge. Similarly, fine-tuning the model is that you're actually train a foundation model, which is a recipient of knowledge. Foundation model usually are open source, like a large language model, like Llama and Mistral, and a lot of them can be actually located at the Hugging Face, the model repository. And then there are some algorithms to fine-tune them. One of the most promising, widely used one is called parameter efficient fine-tuning, or PEFT. So this fine-tuning method tries to not change all the weights and parameter of the foundation model, but only a portion of the foundation model, so that it can learn external knowledge without too much computation cost. Thirdly, about the content it learns. So unlike that, the student can learn from unstructured data like textbooks or something. If you fine-tune a model, you need to do the data curation and you have to make the data structured. So in fine-tuning, people prepare the data in different data schema. So one of them is called question and answer pair. And the other one is called instruction, question and answer triplets. And the final one is called context, instruction, question, and answer quadruplets. So all these design of data schema really, it really depends on how you will use the model in the future, but it's one of the most important factor in the fine-tuning model. And finally, the outcome of the fine-tuning will be a specialized model. So in our case, it's BEMGPT. So this is a general workflow that for us to develop BEMGPT. So you can see the foundation model we use is Llama 3.2, which is also a very strong, powerful model, will be widely used. And in terms of the data preparation, so in our first initial version, we use NH+ engineering reference as well as NH+ input-output reference. Because engineering reference has some physics and also some empirical like equations related to equipment and calculations. So we think it's a good material. And the input-output reference is more about the syntax level of certain software. And then we process like each paragraph or in the documents to become each paragraph will generate several quadruplets. And each quadruplets have the context, instruction, and the question and answer. So you can see this as an example. So this is an example of a quadruplet that we generate. So you can see the context is really about, okay, what's this knowledge like coming from? Okay, this is about knowledge about what topic. It's from the engineering reference. It's from which chapter, something like that. The instruction is about, okay, imagine you are a helpful assistant. So you're trying to be helpful and answer this question in this domain. The question is actually what we expect future people might be asking. In this case, is what objects are used to model air exchange between zones. And the answer is actually the right answer provided to it. So making it as a supervised learning, that making it to learn from the right answer. In terms of algorithms, so we use LoRa. We tried LoRa, QLoRa, and Dora. So these are short for low rank adaptation methods, which are very widely used and turns out to be very effective and widely used in the industry. So the benefit of the advantage of it is very memory efficient, and at the same time, it's also like achieve a relatively high performance compared with full fine tuning. And next is about the results. So after we fine-tune the model, we compare it with foundation model that is untuned, and we prepare some testing data to let it to compare the difference between the expected answer and the generated answer. So we use some metrics, important metrics like Blue, Rogue, and the BERT score to actually decide the distance, like mean the embedding vectors distance between the expected output and the real output to indicate their accuracy. So we do some control variables in this fine-tuning process. So specifically, we try multiple like methodology. For example, we try different fine-tuning methods like LoRa, QLoRa, and Dora. And similarly, we try different data schema. And we find that the best performing combination, which is that we use Dora to train on the like latex file, and then we use the quadruplet as the data schema, and we use Llama 11 billion, 3.2 11 billion, which achieved the best performance. So next, the performance and discussion. So you can see that this is a comparison between the unfine-tuned model and the fine-tuned BEMGPT model. So you can see the question is about what's the role of solar gains in building thermal performance, and the foundation model answered in a very vague way. But the BEMGPT answered in a very detailed way, and accurate way. Let's introduce like, okay, how to cost calculate that? What are the key factors in like affecting it? The second example is about asking what's the infiltration model, how is the infiltration model in NH+. So you can see BEMGPT actually provides detailed like equations that are in latex format with detailed explanation, but the foundation model only just cover very just general answers about it. We do have some bad answers from some results is that you can see in this case, this is our failure answer, that you can see our answer actually generated some equations on the right side. You can see it generated equations that are totally off. It's different from our expected answer. We think it's might coming from hallucination, or it's coming from that it's mixing the knowledge between the knowledge is used to be trained on and the new knowledge we train it to be. So this is some failure results. But overall, that we compare the fine-tuning with retrieval augmented generation. So we find they have achieved similar performance. but the fine-tuning really have better performance in terms of the time to run the results, and also the token used to generate the result, making it a very computation and cost effective. So I really want to highlight that we're not saying fine-tuning and the RAG are one is good over the other. They are not conflictive. So basically we can use both. So you can use fine-tune a model in a RAG structure as a core model to even get a better performance. So basically, the RAG sets the floor, which ensuring the minimum functionality, even the model doesn't know anything. But the fine-tuning sets the ceiling. It defines how far the model can go to being expert or can be reasoned and to solve more complex tasks. The fourth is how we open source the model. So we publish it on in Hugging Face. So this is a QR code that you can scan to check our code on Hugging Face. So it includes both all the fine-tuned models, our curated training data, and our example code to actually run this model. Finally, some conclusion in the future work. So basically, we developed the first version of BEMGPT, and we tried very different fine-tuning method, data curation, and the foundation models, and we select the best performing combination. And we find that our outperformance foundation model over 50%. And we'll also find that the data curation actually is the most time-consuming part of doing the fine-tuning, and also the most important factor to impact fine-tuning performance. So in the future, we definitely will include more training data, since here we only have 2 super long documents, but we needed to further enrich BEMGPT with more data sources. And finally is that we think that the reinforcement learning, reinforcement learning fine-tuning is actually also a good techniques. It's better for advanced reasoning, but we just find that it's not, in terms of knowledge extraction, it's not as good as supervised fine-tuning. But we haven't tried it for the reasoning part, so this is our future work. Finally, is the benchmarking. Since I believe more and more like specialized model in BEM will appear soon in the future, so standardized evaluation metrics and the standard test set are actually needed. Thank you very much for your attention. So that's all for my presentation. So I think so the question and answer will happen after Dr. Jain finish his presentation. So I'll just stop share now.
Awesome, thank you. Should we just transition to ours now? Is that?
Yes.
Yeah, okay, perfect. All right, well, thank you very much. So my name is Rishee Jain. Dipashreya is also here. She's the awesome PhD student in my lab who's actually leading this work. So what I'll do is I'll give a quick introduction of what we do in the Stanford Urban Informatics Lab and a general sort of high-level overview of this work, and then I'll pass it to her to tell you all about the hard work she's done. So what we're trying to do in this work is actually understand the feasibility of using prompt engineering, which is a form of input into these Gen AI models, to actually develop complex building energy models. And so can you actually help it speed up the process of building a model? The next slide. Okay, so just taking a step back. So I direct the Urban Informatics Lab, and basically what we do is analyze data to model interactions between human buildings and energy systems in cities. And I underline human here, as you'll see a big aspect of what we're trying to study here is the feasibility and the human-computer interaction component. Many of these Gen AI models are pretty phenomenal, but unless they can fit into our workflow as building energy modelers, they're not as valuable to actually make an impact in the field. Next slide. Awesome. So as many of you know, I'm preaching to the choir here that, we need to be able to build building energy models at scale if we're going to do anything relevant in the decarbonization efforts of the built environment. And we take a bunch of inputs, geometric information, non-geometric parameters. We put them in a simulation tool. We try to build a building energy model, and we try to do some analysis to identify sources of energy waste. What could be done? This could be done post-occupancy to understand for retrofit decision-making and operations optimization, or even in the design phase as things are happening and what design changes we could do. Next slide. But the challenge is it's expensive, it takes a long time, and there's usability issues with BEM. think we've all faced this. It takes a long time to actually build a building energy model. It can be very expensive if you're trying to do this at scale. And there's a steep learning curve for new users. And actually, Eric, who's co-hosting this with me, actually teaches our fundamental building energy modeling class at Stanford. And we've seen this, upfront and personal, is that when we teach students about this and how to use things like OpenStudio, there's a huge learning curve. They spend the majority of their time trying to figure out how to go from plans to a basic energy model, and actually often run out of time to do analysis and critical thinking of the results. So our thought here is, can we use Gen AI to speed up that manual process so students and building energy modelers are actually thinking about the output of these, and then connecting the feedback loop on how they can make decisions. Next slide. So we're not the first to try to think about how you can automate the model development process. So there's the building component library that's incredible, that has 30,000 plus predefined components. And then there's even DOE prototype buildings, as everybody knows here. 786 templates. We're building on top of this. The challenge of using just of these is that they often can't capture the uniqueness of each individual building. You still have to make significant modifications. So we're trying to take these sort of starting points and take them forward using Gen AI models. Next slide. So Gen AI presents an opportunity to address these scalability issues. How do you take where we've started with the building component libraries and the DOE foundational models, and then take them to the next stage here? And so, as was in the previous presentation, Gen AI is a great tool. It can create new content based on pattern identification and reproducing trained data. There's all these things like large language models, and then there's even AI-powered assistants. So our idea is how we take these large language models, because effectively an Energy Plus model is a bunch of text. Can we utilize it to automate this process? And so with that introduction, I'm going to pass it over to Dipashreya, who's going to talk to you about some analysis and a study we did to actually look at if this is possible and what the challenges are.
Thanks, Professor Jain. So contextualizing this intersection between Gen AI and BEM, we see that prompt engineering large language models has shown effectiveness for simple BEM cases. Case studies have shown the promise of using chain of thought prompts that guide the large language model through a step-by-step process to generate your IDF content, including people and zone objects, and more simple rectangular building cases. The challenge, though, with this approach of prompt engineering is that it is yet to be explored of its ability to capture more complex building cases, going away from those simple rectangular buildings to buildings with more complex geometry and multiple thermal zones. Also, there is an opportunity here to look more into multimodal large language models like OpenAI's GPT-4o and how it can automate the extraction of key information from architectural and mechanical plans. And this incorporation could really help streamline the BEM process and address those issues we discussed earlier. So building on these different challenges and opportunities, we developed a feasibility study on multimodal prompt engineering for complex BEM development. Our study focuses on 3 main stages. The first stage involves developing multimodal data inputs. We developed prompts that were only textual, only visual, and combined. The only textual prompts include building material names for the construction, geospatial data for geometry, thermal zones lists, space types lists, and occupancy schedule descriptions. The only visual prompts include architectural and mechanical plans, and for the occupancy schedules, plots of the daily schedules. And the combined prompts take the textual and visual prompts together to see if incorporating both modalities actually increases the LLM performance. In the last 2 stages, we focus on input processing and the calibrated building energy model. Specifically, we do a cross comparison to calculate the match between the large language model and a calibrated model. The industry standard calibrated model that we use was developed in Naeem et al. 2025 and meets the ASHRAE Guideline 14, which provides for us a robust comparison. To do this comparison, we calculate the percentage match across 5 individual components: space types, occupancy schedules, geometry, thermal zones, and construction. And we set a benchmark of 90% to ensure that there's some accuracy while also accounting for slight discrepancy between the two outputs. Now we will go a little bit more into the evaluation factors and the key metrics used for each component. For the building geometry component, we wanted to ensure that the large language model output could capture the size and complexity of the test building. So we compared the floor area, wall area, window area, and footprint perimeter between the large language model output and the test building floor plans. For the building construction, we analyzed the material thermal conductivity and window fenestration values across 16 construction objects between the large language model output and the calibrated model. For the thermal zones on the large language model front, we got to the stage of developing reference points. So we calculated the Euclidean distance between the large language model output and the points on the calibrated model. For the space types, we analyzed the large language model's ability to complete all 48 objects. And for the occupancy schedules, we calculate the frequency of the load shape patterns for 4 daily schedules between the large language model output and the calibrated model. Since we've walked through more of the evaluation factors, let's go through some examples of the given prompts together. So here's an example of the first prompt in the building geometry component that focuses on extracting the building footprint. All prompts begin with setting the context of assuming the role of a building energy modeler. They end with a template of the IDF object to also reduce any syntactical errors and ensure that the prompt output could be run in OpenStudio. In this case, the IDF template includes the floor object. What really varies, though, between these different prompt modalities is the task itself. The textual prompt asks GPT to transform the geographic coordinates of an OpenStreetMaps file to output the building footprint. The visual prompt asks GPT to analyze the annotated floor plans provided for the building footprint. And the combined prompts ask GPT to run the textual prompts and then verify the outputs with the plans. Walking through another example, this time in the construction component, we can see the same trend occur for determining the material R value. In this case, the template included is the material IDF object, and the task in the textual prompt includes asking GPT to determine the R value from a list of materials. This actually attests OpenAI's building material knowledge to see if the given R values actually match the calibrated model. For the visual prompt, we asked GPT to determine the R value of labeled materials from annotated section drawings. And in the combined prompts, we ask it to first run the textual prompt and then verify the output with the visual prompt. And for our third example, we can look through the thermal zones component and defining the reference point. For our textual prompt, we asked GPT to define the zones using the AutoZoner method developed in Dogan et al. 2016. Here, we actually ask it to do it based on its own understanding of the method to see how GPT understands different methods developed within the BEM community. For the visual prompts, we ask it to define zones for an annotated footprint. And for the combined prompts, we ask it to first run the textual prompt and then verify the output with the visual prompt. After we develop the remaining components of the space types and the occupancy schedules, we calculated the mean percentage match across the three categories of textual, visual, and combined. We found that the textual prompts show the highest mean percentage match of 93.6%, while the visual prompts showed 74.2% and the combined of 89.6% of a mean percentage match. The visual and combined prompts are much lower in their percentage, predominantly due to the building construction and occupancy schedules categories. Now, this run was all done for just one run of GPT, so we became curious of what occurs if we take the best performing prompts, or the textual prompts, and run them multiple times. To do so, we did these different runs, and we calculated the root mean square error, or RMSE, to really account for larger discrepancies that may be occurring in the percentage match. We found that the thermal zones had the highest mean RMSE of 0.19. The building geometry had 0.17. So these are both areas where there's more prone for hallucination or errors to be occurring. The construction component showed some RMSE of 0.06, so some slight variability, while the space types and occupancy schedule showed consistency with a mean RMSE of 0. So now that we've walked through some of the results, I'm going to hand it back to Professor Jain to conclude our discussion.
Awesome. Thank you, Dipashreya. So, this work was just a starting point to really understand the feasibility. And so future work aims to address a couple of challenges or limitations of this work. First of all, we didn't really capture interdependencies between BEM components. As we all know, when you tweak one system, say the lighting system, it has impact on the cooling loads and the heating loads. And so that's where we need to further develop the study. We also want to think about developing textual prompts for templates for new construction scenarios, so different types of scenarios. And then finally, we're actually doing this now. We're conducting a usability study to actually compare the experiences of using prompt engineering to traditional BEM. And we're running these sort of controlled experiments where we're giving energy modelers an exercise to do to understand what are the trade-offs. There is still a learning curve with using Gen AI. Where are the benefits? Where are the challenges in using a traditional sort of workflow? Next slide. All right, so where do we go from here? So, the future, and this is where there's still a good amount of research and development that's needed. But, the future, we view that what Gen AI can enable is something like an AI-powered BEM assistant. This could help troubleshoot and operationalize models. I think everybody here has spent way too much time hitting their head against the wall, trying to find a bug in their model, something doesn't make sense. Could we enable that to be sped up? We've seen this have a dramatic impact in the software engineering space with GitHub's, Copilot and other Gen AI tools that have helped software engineers find bugs faster. We should be able to do the same thing. And the goal is here is to enable building engineers to spend more time on analysis and decision making, not on model building and debugging. And then another place is what we saw in the earlier presentation by Professor Zhang on foundational models. And I put foundational in an air quote here. If you talk to an AI engineer, a foundational model is like ChatGPT or Llama. This is what I'm talking about. This sense is fine-tuning the model to enable training-free models for design and operations. Specifically, I think we need to think about how we break these two things apart. If you're doing a design problem, it's very different versus if you're doing an operations problem. Design problem, maybe you want to speed something up so you can quickly spool and look at different scenarios. If it's operations, you really need a very fine-tuned model that's specific for your building if you want to actually translate to use BEM into operations. And then finally, a challenge that we've heard when talking to many architects who many of us work with is that it's very expensive and challenging to make tweaks in a BEM model very early in the design phase. But they can have substantial impacts. Decisions made by architects and designers can have big impacts down the line. Can we lower the cost of entering this space so we can have even very simple models to run different scenarios to allow designers to make trade-offs early on in the decision-making process, and instead of waiting too late when things have been locked into place. And then, often as building engineers, we're trying to make the best solution given the current design decisions. So with that, next slide. We'd love to take questions, comments. Our emails are here. If you're wanting to get engaged on this work, we're always looking to for practitioners who are willing to try these tools and help us study what's working and what's not working. I think as in many things in the AI world, there's a lot of over-promising and under-delivering maybe a little bit. But what we need to do is, I think the motivation there is we need to figure out what's working and what's not so we can build innovative tools on top of it. Awesome. And I think we're going to open it up to questions now.
Awesome. Thanks for both our speakers. And I think some questions coming in for sure. And I will read a couple of them. Yeah, I think this is a relevant one for Dr. Jain. And so this is from Karen Walkerman. Karen, do you want to ask a question or? Okay, I'll just read. So Karen's question is, I'm curious about the generating building outlines and floor plans from drawings. What level of details was included in the images prompts for the building geometry and thermal zone in your study? And yeah, that's the basic question for you, Dr. Jain. And
yeah, Dipashreya, do you want to tackle that first, and then I can add on? on the
Yeah, that sounds great. That's a great question. For our study, we followed architectural graphics principles. So for the building geometry aspect, we annotated the floor plans, demarcating the key building dimensions. For the thermal zones aspect, we took a building footprint and we labeled like different rectangles for where the zone should be located. But there's definitely room for further exploration to see if certain demarcations or outlines and graphics actually improve those performance of the visual prompts.
Cool. There's a second part of the question, actually, for both teams. What has been your experiences using the different LLMs? Why do you prefer OpenAI versus other LLMs?
Maybe I.
So, John, do you want to start?
Yeah.
Oh yeah. So yeah, it's a really big question. So yeah, because there are so many thousands of models out there, and it's sometimes hard to choose. But one of the things you need to consider is about cost. So it depends on the complexity of your problem is. So if you just want to let it to you don't have too much coding experience, or you don't want to do something about that, just using the OpenAI, because they are not just a pure foundation model. Actually, they embedded a lot of agentic workflow over there. When you type something in the web page, they will just call off agents and stuff so that it will answer your question perfectly. So it's not just a foundation model anymore when you type in the web interface. So if you have this kind of like daily, like uncoded required thing, just type it in just using some commercial tools like OpenAI and Anthropic. But if you are talking about you're embedding your LLM in your agent workflow, or you want to have it in a more like automated procedures, so you really want to look at the size of it, whether it can deploy it in your local machine or in your on the cloud server, so that you can consider the cost. And also you want to think about whether you want to use open source or closed source. So open source, usually you can just use your own machine. Like our lab, we have a AI workstation. We have 80 gigabytes of VRAM, a GPU VRAM. So making it we can run everything without any cost. But if you want to call API, it's relatively expensive. So but in terms of performance, it's definitely these large models usually have better performance. So I don't have a systematic study on it, but this is my general impression. Like it's really my perspective is considering your complexity of task and also your budget. But that's all. Yeah.
I think I agree. I think we can move to the next question. It's pretty much same what we're doing. I think we're trying to try the different models to understand the trade-offs. As you've seen, each of them promises different aspects. Some are a little bit more open source, like Llama, and so there's just these different trade-offs that will occur. And I think as more and more studies come out, we'll understand which ones are better suited for applications in the building energy model community.
Yep, awesome. Here's another interesting question about the security. So Alex Zoka, and question is, to what extent have you worked on seeing others using AI to build or assemble models in BEM programs? How is this achieved? How is the security of client data managed?
I'm happy to go first, and then Fresh saying, do you want to take it after? Okay, perfect. So I think that this is still a very much an open question. So great question, Alex. I think, the goal is that one could see in the long term is that we develop these fine-tuned models that could then be spooled up individually for a specific client. So you kind of have an interface that exists between what is general knowledge on one side that is train the model, and then what is specific knowledge to your project that is private and confidential client data. We're not quite there yet because we're still needing to train the general knowledge models to get better and better. But at some point there would be this interface. We see this happening, in the software engineering industry with colleagues that I know that work in that space, where they have these foundational models that help. especially on the open source part of it. But then as it gets into private confidential side of the code, they spool up smaller models that can then work on it. So there's kind of going to be this interface that exists if we take the analogy for how it's worked in software engineering.
Yeah, I also agree. And also I just want to mention one keyword is the MCP, the model context protocol. It's actually designed to actually protect data privacy. So basically, you will have an MCP server and you can deploy it in a private machine or something. Or even it's a cloud. So MCP protocol will help to like protect your data privacy. So just add something to Professor Jain's comments. Yeah.
Yep. The next question is from Rajiv Kosa. And the question is, I think it's more for you, Dr. Zhang, on the fine-tuning. So data curation looks like the most painstaking step when it comes to training the models and result generation. Do you have any takeaways from your work on the curation aspect?
That's a super good question. So that's exactly what we're experiencing. So my student Mike Fu is also in attending this. You can see him. So so we did a lot of trying. Actually, like we said, we try different like data schema, like question and answer pair, or the instruction question answer triplets, 3-element, and this kind of quadruplets, like 4-element stuff. So it's more about like trial and error. We just try different data like preparation method and feed it into model and see how it works. It's just like a trial. We don't have any. Actually, it's very hard to tell how to do that from the beginning when we don't know the answer. So yes, it's a painstaking step. But I think to answer your question, based on if you have enough like a memory in your machine, you can do super long input data. So you can start with doing the quadruplets, which is a 4-element data schema, like the content instruction question answer. And if you feel it's good, you can just reduce the size of it until you find that the performance won't change anymore. So this is I think this is what my takeaway. For our case, the quadruplets actually works the best. And also I see another similar question in the chat about asking how I generate the quadruplet data sets. So yeah, that's a great question. We use another foundation model. We use GPT-4o model to actually extract the latex document, latex format from NH Plus like GitHub repository. And we let it just tell it, we have a prompt about, okay, generate as much as droplets you can find from this paragraph and prepare the data for me. So basically, we use another GPT to generate that training data for us. And because it's too expensive for us to extract them manually. So hope this answers your question.
Thank you, Dr. Zhang. And next question from Pratik Wahi. The question for both of you. As a building physics practitioner, I often encounter challenges related to the performance gap between simulated and measured data. This issue is becoming increasingly critical, especially as we strive to design buildings that are Paris-proof. Do you see potentials for generative AI to help reduce this performance gap? If so, in what ways?
I'm happy to take this first. So I think, especially in our work is, the challenge that I think often we've seen is that you spend so much time actually trying to build the first initial iteration of the model that you're not spending a lot of time on troubleshooting to how to get it to better align with the measured data. So I think we're hoping to speed up that feedback loop. So when you see this performance gap, it's not going to go away. Maybe we can get rid of some of them with, more advanced, construction or a better process with Gen AI to build the initial model. But as it actually is that we want to, speed up that feedback loop. So you can make 10 iterations to actually get closer to your measured data based on your simulation, rather than only doing one iteration and sort of running out of time or resources or both.
So my perspective is from that, because I think doing the the gap between simulation and measured data is the nature of building edge modeling. So it's about I think generative AI might be another good solution to solve this problem. If because of the nature of building edge modeling, I believe. So it's from physics-based models, but you cannot never describe these uncertainties and inaccurate description of the building to reflect the 100% truth. So I believe generative AI is not like can do anything. But if you talk about doing calibration to really gap the difference between model and the data, actually generative AI can actually automate this process. So I see some paper actually doing this stuff to build like agentic workflow to like automating the calibration process. Like anything that you do as a modeler, it can repeat, it can duplicate or learn how modelers do that and put it into agentic workflow to actually build this workflow to actually automate this process. So yeah.
Okay, thank you. The next question is from Mohammed Al-Rawas. What about the compatibility of AI with market BEM softwares? I guess the question is about I guess the study is really using NH+, which is open source. What about some of the like commercial grade softwares like IESVE or Design Builder? How does the compatibility of AI with those softwares?
I'm not sure I understand this question very well. The compatibility of AI.
Mohammed, you can unmute yourself if you want to speak to it.
Okay. All right, maybe let's move on to the next question. Unless someone of you are wanting to try to answer the question. I think it's about how can we using the AI models to the compatibility issue between AI models and like commercial grade softwares.
I think it's always needs engineering to make it fit to different BEM software. Depending on the very different nature or mechanism or just methods or interface of different software. So you need to, if you want to have Gen AI to work for each of them, you need to design this workflow very specific to each individual BEM software. So I don't think there will be some like one fits all scenario here. So I will say there's very poor compatibility. We have to customize or doing engineering on each of different BEM software.
Good. Thanks. The next question for BEMGPT, are you giving away confidence scores for the answers? Being new to the BEM, how can I find the model is giving correct answer or hallucination answers?
That's a very good question. So when we do a testing or like we try to understand the training error and the testing error, we do use some metrics like a BERT score, so which evaluate the like the embedding vector distance between, which meaning how different these two answers are, how far away these two answers are, the true answer and the predicted answer. But when it comes to the use of the model, hallucination is the problem that it hasn't been solved, and I think it's all beyond my expertise. But there are some ways to actually deal with hallucination. One is people will always the final loop in using generative AI, just like you use the ChatGPT to generate something for you, and you always review it before you send it to someone else or you use it by yourself. So a human will be someone that can be the last agent that can check whether the answer may be correct or not. But for a beginner, like for example, for people who never who just start to use BEM and not know too much knowledge about BEM, I think this is somehow a big issue. But there are some ways to solve it. One is that if the model can actually generate the source of the information, for example, when it answered a beginner of BEM, it tells him, okay, this information is come from this document in this chapter and this paragraph. So that in order to validate whether it's right or not, the beginner or the BEM modeler can just go to the document and check by himself. So that's why we designed the training data to have context when it is preparing training data. Is we want to tell the modeler, okay, where might be the true answer come from. But for now, we don't have a really good method to automatically like validate or check whether there's hallucination. So our method is that provide the user with more information to let them check by themselves. Yeah.
Awesome. Another question for Dr. Jain and Dipashreya. The Stanford study being discussed here documented in a form or report or paper. And yeah, we'd like to learn more about it.
Yes, absolutely. That's a great question. So actually, Dipashreya will be in Building Simulation 2025 in Brisbane in a few weeks to present this work, and it'll come out in the proceedings. So please stay tuned and look out for that.
Yeah. Okay. Oh yeah, I just realized we couldn't really unmute the attendees, and sorry about that. We got just read questions here. I think maybe another final question for Dr. Zhang. As I said, interesting question, so maybe it's be recorded. So given that many training data sets come from the buildings in the regions like North America and Europe, how do you address the potential biases to ensure that BEMGPT or other BEM AI models scale effectively to regions like Global South, and where climate and building types can differ significantly?
Yeah, that's a good question. So I actually answered it on the answer, but I will just repeat. So basically, that's why we actually, when we fine-tune the model, prepare the training data, we added the context into the training data. We want to let it know where this knowledge comes from. So you said that, okay, it's from North America or it's Europe. So this information can be embedded in your training data in the context part, saying, okay, this is about North Americans building code, or this is from not Oxford, but some other like elsewhere, like whatever is from Europe, which standard. So in this way, this information will be learned by fine-tune model, so that it can at least when it's generate results, it will just remind the user where the information source of that hopefully can reduce the bias. But it's a good question. And because even this, it cannot really fully solve this problem, because bias issue is always a big issue. So that's why people need to do alignment. So it's called technical alignment in a large language model, is that you are actually like having some, no matter it's about reducing the bias of region, or you have some dangerous like statement or something like that, you need to have alignment to actually to make it more, how to say, unbiased answers to people. And this include a lot of like human related efforts. Like you need to actually use a human to actually do the with human feedback to reduce this kind of bias. So yeah, that's my answer to the question.
Awesome. Thanks for all the questions. I think we're right on time, and thanks for all our speakers, and thanks for all the attendees joining us today. I will take the last minute to introduce that, just a reminder that the abstract for SimBuild 2026 is due by August 4th, 2025, which is next Monday. So, we encourage you to submit your work to join our growing community of researchers and practitioners. And again, thank you for joining, and have a wonderful rest of your day. Thanks all.
Thank you.